Hello, this is Vivek, and in this particular video, we'll talk about greedy. So, a lot of people come to me and say, Vivek, teach us ad hoc, teach us greedy. How do we solve such problems of ad hoc logic and stuff? How do we solve observation based questions? How do we solve greedy questions and all, right? And I sometimes feel people expect me to create a roadmap on these, whereas nothing like that can ever exist. Because if it would have been so simple, everybody would have become good at it, right? So, there is a lot of, like, I'd say, observation practice that has involved. A lot of proofing is something that helps in this. But then I feel there are like 30-ish, 37, 38 different ideas in greedy, right? That kind of repeats quite often, and not just at beginner level, also at an like expert or candidate master level. They kind of get repeated till that rating range too. And then if you know these ideas, you will be able to progress very quickly. What I will do is I will create a series. Slowly, I will keep putting more and more of these ideas as I come across them. And this is going to be the first video of that. I'll teach you a technique where you will learn about one of these techniques of greedy that helps you solve a class of problems. Let's talk about it. Chalo, let's start. Okay, so this is episode 1 of Beautiful Greedy Ideas, right? And the theme today is what you can't create, right? So, what exactly the problems look like? So, the problem that will be given to you is, given a set of n numbers, find the smallest number that you cannot create out of this n element. So, let's suppose you are given 1, 2, 1, 7, 6. What is the smallest subset sum that you cannot create? Now, I can create 1 over here because I can just take 1. I can take 2 and I can create 2. I can take 1, 2 and I can create 3. I can take 1, 2, 1 and I can create 4. But can I create 5? Obviously, like, things beyond this will not help me. But if you take things like 1 to 1, you can create till 4 only. So 5 is the smallest number that we cannot create. So answer for this will be equal to 5. This is what you are expected to find out in this problem. Now we will do multiple level of this, like not just very simple question like this, but also to a level where you will absolutely enjoy learning harder ideas, right? I'll take you from very basics to the advanced. Now, the very first idea that you can solve this is using maybe DP. I hope you know what DP is. So there is this famous problem called subset sum, no? Where you basically try to keep DP of level, comma, sum created or left, right? And you can solve using this. If you haven't seen my DP series, this is basically form 1. And if you use form 1 formulation, this is very simple to solve, right? You can just create level and then sum create or sum left. And then you can solve this problem very easily. Now, what you will end up getting is how much sum you can create. For all of them, you will get, if you use, forget about this. If you use sum left, you can create DP of 0, comma, any particular number, and it will tell you 0 or 1, depending upon can you create this much sum or not. Okay, exactly this sum or not. And using that, you can solve this problem, and it can get to a like O of n into sum of A of I kind of complexity, maybe, right? Every element you'll have 2 choices, take it or don't take it. But the problem with this is the question that we are taking at our hand, the constraints are much, much larger, okay? So I'm assuming that n is up to 10 to the power 5 and AIs are up to 10 to the power 9, okay? That's the problem that we are dealing with right now. So in that case, this is not an option, but then you could have used subset sum DP. If you don't have no idea about this, please read, just Google subset sum DP. You will get tons of blogs, tons of videos on it. If something already exists, there is no point in me creating that separately. But some set, some DP is something that can solve this, but not in the complexity that we want. Okay. Idea 2, right? So what if we need up till n 10 to the power 5, which means something greedy, no? Something sorting. So whenever you have a subset generation, very simple like idea on greedy, if you have to generate subsets, and subsets means no ordering, right? Subarray means ordering is there. So when you have to generate subsets and constraints are high, most probably you are dealing with some sort of sorting problem. So it's wise to think about it in terms of sorting. 1, 2, 1, 2, 6, 7, right? But then still after sorting, you have to think about how you can solve. Okay. Now, there is a very interesting greedy idea that exists for this problem. You start from the start, 1. Okay. Can I create 1? There is a 1 directly available. Only then I can do it. If everything is bigger than 1, then I cannot do it. So if I can create 1, the next element I want to look for is 2. Okay. I can create 1. Can I create 2? Yes, because there is another 1. So till now the sum is 2. So since the sum is 2, I can take all the 2 elements and I can build 2, no? Okay. So till now I can generate 1, I can generate 2. I can generate up till 2. The prefix sum is up till 2. So I can generate only up till 2. Next element is, I have generated 1, I have generated 2. Okay. Using just the first 2 elements. Now I get 2. I can generate this plus 2 and I can generate this plus 2 now. So I can generate 1, 2, 3, 4. And that is up till prefix sum. Okay. Then the next thing is I have generated 1, 2, 3, 4. I'm getting 6. So I can generate this plus 6, which is nothing but 7. I can generate this plus 6, which is 8, and so on. So you saw that we got a hole over here, right? So if you see it very closely, how exactly are we expanding our set? Whatever we have a prefix sum till, okay, whatever we have a prefix sum till, or whatever subset sums we could generate, all of them are getting added with 6 and getting added to the list of subset sums that we can generate. So a very simple greedy idea that you can use in this problem is go forward one by one, go forward one by one. Okay, like if you have to code this, it's very simple to code. Maintain prefix sum array, right? You can build the prefix sum on the go, but basically it will look like 1, 2, 4, 6, 7. You have to see the first element has to be equal to 1 because or else 1 cannot be created, isn't it? Now, since 1 is created, the next element has to be greater than equal to 2. Okay. The next element has to be equal to 2 because, sorry, I shouldn't write this as greater than equal to 2. I think what you should think about it this way is the prefix sum that you have built is 1. Now, you need to create 2. Either this is 2 or this plus the previous element is 2. So you have this as 1. So it is fine. So you build till 1 and now you have built both 1 and 2. Okay. Now, the next thing that you want to create is 3. Now, either you should be able to extend all of the previous things by whatever is the next element to create 3 somehow, or else it's not possible. So 2 is present. So all of these things can be extended to 3, 4. So 3 is now covered in the range. Okay. Next is 6. So all of these things will be possible to generate after plus 6 kind of a range. So there is a whole of 5 which you can never generate now. So the idea over here is you maintain that what numbers you have created. You have created 1. If you get a 2, you can get 2 and you can extend everything previously built by 2 plus 2. Now once you have 2, if you let's kind of add it over here. Let's take one another array over here just to an example. 1, 2, 4, 5. Okay, let's start extending using this. 1, you can build subset sum of 1. Then 2, when 2 comes in, 2 can build itself 2 plus 0 and 2 plus 1. So 0 and 1 are there already. 2 plus 0, 2 plus 1 will be 2 and 3. Then when 4 comes in, all of these things plus 4. So 0 plus 4, 4, 5, 6, 7. Then it's looking for 8. You get 5. So all of this plus 5. So 0 plus 5, so on. So all of these things will be overlapped, but that is fine. So you can generate 8, 9. So 5, 6, 7, like 7 plus 5, which is 12. Okay. Let's say this is 13. So now you're looking for 13 right now, right? Because you can generate till 12. The prefix sum right now is till 12. So you're looking for 13. If the next element is 13, that is good. If it is not, then you can never generate 13. If it's 14, you cannot generate that. If it is 12, then you can generate because 12 will come below 12 and it will extend the rest of the range because you're looking for 13 as of now, right? But if the next number is bigger than 13, so 0 plus that number cannot give you 13 and anything previous also extended with that is not going to give you 13. So you can never generate 13. So basically the greedy idea right now is generate till a certain range, whatever you can, okay, and see if you can generate the next number. If something comes in this range, you extend this further because every number over here is possible. So all of that plus some constant will only extend this number further. So you maintain a prefix sum for that. But prefix sum plus 1, if something comes beyond prefix sum plus 1, you cannot create that number. Okay, that's the greedy idea over here for this problem. Well and good. I think that's a fairly good idea to solve. But then this was 12 over here. But then there came this really good question that I saw on CSES, okay, which I'm going to take up next. Is this same question that you have n coins, they are numbered x1, x2, x3 up till xn, right? Indexed 1 to n. But there are queries, okay? There are queries that you have to solve wherein you have to find, if you use coin A to B, what is the smallest sum that you cannot create, okay? And this problem was something that took me an hour to solve, even after I knew the previous logic, okay? So the previous logic was something that I saw in like maybe 5 years back in some code chef long, if I'm not wrong. But this is something that actually was a little difficult in a sense that I couldn't really extend the previous logic to this, right? Because you now have to do it for queries. Now, what do you save, right? Now, when you see queries, two things kind of comes to my mind immediately. Prefix sum because they are static, right? Or maybe you can maintain something with prefix sums. The second thing is maybe segment trees, right? Because there are queries. Now, the question is, how do you maintain these things in segment trees? Because if you think about it, we can't really generate anything in that range, you know, because we have to always check. This is an iterative process from start. You have to take that range, sort it, and then see 1 is present, then less than equal to what is present, if something is present or not. If it is present, fine, then extend it. Less than equal to, then whatever that comes, less than equal to 3 is present or not, and all so on, right? So if your prefix sum is still p, you look for p plus 1, something less than equal to p plus 1. If it is there, so the logic, if I have to close down the logic, sorry for not doing that, prefix sum equal to 0, current equal to 0, for current equal to 0, current is less than equal to n, less than n, current plus plus, if I have to write this, okay. If ARR of current is less than equal to prefix sum plus 1, right? If it is less than equal to this, then you are possibly able to create that number, so include it. So prefix sum plus equals to that ARR of cur, or else answer equal to prefix sum plus 1, because you have gone beyond that, so it's already sorted, right? That's basically the idea. But then I read this problem and I was like, okay, how will I extend that logic to this? And I kept thinking about it. I kind of used all my segmentary ideas that I ever had learned and thought about it, but I couldn't really think about how you can extend that idea to this problem, right? And it turns out that there is actually an idea 3, which I kind of, after 30 minutes, I thought, okay, let's switch off every mode now. Let's think about it from scratch. Let's say I don't know the previous logic. How can I kind of solve this problem? And something was clear to me, that since it is segmentary, in a node, you can generally store either a single number or you can store 30 numbers. Maybe something goes with bits in this problem. So I was exploring that option. That's how you kind of start exploring things. So what I came across is this: there is this idea 3 to solve this problem, okay? That you look at this whole problem, that there is a small hole, right? So 1, 2, 3 up till 10, 12, there is a hole that you cannot create 3, you cannot create 5, some number, right? There is some number as a whole which you cannot create. This you can create, this you can create. There are some holes. Note that you cannot do binary search, because this can be done, but this cannot be done. So it's not a monotone space. Sorry for not mentioning this. I think a lot of beginners will find this as binary search problem, and then it's not actually, right? So there are certain holes which you cannot create. So the idea for this problem is you look for which power of binary does that whole line. Okay. What does that mean, Vivek? So you have 0, which is separately there. This is 2 to the power 0 bracket. This is 2 to the power 1 to 2 to the power 2 minus 1. Then, so if I have to write this, 4 over here. This is 2 to the power 2 till 2 to the power 3 minus 1. Then 8 goes beyond, right? So I can create these buckets over here, no? 2 to the power I to 2 to the power I plus 1 minus 1. This is like the ith bucket. Okay, this is the ith bucket over here. How do we use this? How do we use this to solve our problem? Now what we are looking for is what is the smallest I where you have a hole? Okay, that's the idea that we'll use. That the first hole lies somewhere over here, let's suppose. So it's in this bucket. So we need to find this, which bucket it lies in, right? And for each bucket, we'll try to find its first hole. Okay, wow, how do we do that? Well, firstly, when you are looking at a particular bucket, right? When you are looking at this particular bucket, every number that is over here are accessible to you, right? Like forget about range right now, forget about range and all, okay? So over here, if you're thinking about a certain bucket, let's suppose this bucket, 2 to 3 range, okay? So every number that is less than 2 is of course available to you, okay? So all the ones are available, right? Because they are in the range. I'm assuming this is the range for now. Forget about the query version. Think about just as an array. Only the one versions are available. Only the numbers available less than query are available. So you have all the numbers less than 2 for now. The sum is 2. So if there was no hole over here, you could create till 2, okay? Now what you're looking for is a number 3, because you could create till 2 in this zone itself and you didn't had a hole, let's suppose. So in this zone, you're trying to see where can be the hole. So if till 2 you can create, maybe the hole is at 3, and that is what you check. Is the hole at 3? Now, since you have already included everything over here, you just try to see, is there a single element less than equal to 3 available in this array that you have not considered in the previous layers? Let me make this diagram a little more clearer so that you can understand it a little better. So we have a bucket of 2 to the power 0, which is nothing but 1. We have a bucket of 2 to the power 1, which is 2 and 3. 2 to the power 2, 4, 5, 6, 7. Okay. So what you look for is, you look for in this bucket, obviously like 1 is present, so we can do that anyways the ad hoc way. But in this bucket, you see what were the things available in this range or in this array, which are smaller powers because there were no holes in it. So you include all of them. So till 2, you can make a sum using those elements. 1 and 1, 2 you can make. Till 2, you can make a sum. So what you're looking for, if a hole will exist, it will exist at 2 plus 1 equal to 3. So what I want to find is, in this range, is there an element less than equal to 3? Because if it is there, then the previous sum plus this number, so any number over here, okay, plus something that exists in this range, if a single number exists in this range, it will cover till this much. That's the beauty of this idea. See, think about it. If you have even a single number till over here, like 2 to the power I minus 1, right? Or every range has been filled. So at least one element of every bucket was there. Okay. And then you have 1 in this bucket also. So you have 2 to the power I also, some number 2 to the power I in this range. Everything is bigger than 2 to the power I, 2 to the power I minus 1. So this sum is also equal to 2 to the power I plus 1 minus 1. So you will cover till this much range. That's the idea. Every bucket needs to have at least one element in them present, or else this will not be possible. Or some of the previous buckets compensate for that element. That can be possible, but that's the rough idea of proving it. So you see that less than equal to 3, anything exists in this bucket? Yes, 2 is present over here. So you can make this bucket. So now you try for this bucket. The smallest number is 4. So you look for elements less than equal to 4. So you have 1 plus 2 plus 1, which is equal to 4. So you can make till 4. You look for 5. Is there an element in this array which is less than equal to 5? It turns out no. In this bucket. So you say that 5 is the element, that is the answer. Okay. That's the main idea for solving this problem. Now I know this is super hard to think about on your own, but then this is the beauty of this problem, that you look for buckets of 2 to the power I. Now this is a hard problem again, but then I hope that you got the idea. Let's look at a little bit of code for this. Then only I think it will make sense. How do you do this in segment tree? So to code this for segment tree, we will maintain certain things. Number one is you will maintain sums in each range. So you will have bucketing for 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on up till 2 to the power 30, whatever like is the range of elements in the given array. You can maintain how like the sum of elements in this range, sum of element in this range, because when you are considering this bucket, all of these are present. So you need to get their prefix sum, no? So all of that will be available using sums. So you can maintain sums over here, and you can maintain the minimum in each bucket. What is the smallest element in each bucket? That in 2 to the power 0, what is the smallest element? What in 2 to the power 1, what is the smallest element? In this bucket, what is the smallest element, and so on. And so you can maintain all these minimum elements in over here. And that will be your node structure. That will be your node structure, and you can merge two node structures. How will you merge? If there is two node structure being merged, the sums for 2 to the power I will add, the minimum will get minimum. That's how you merge the two nodes. Okay? That's the basic idea of how you merge in this case. Let's look at code. That will be much more clearer. So this is the code that I wrote at the start. The node structure has sum of values that are in the range and minimum present in that range. So for everything you have till max I've maintained till 30, and you will have 0 in all the sums, and minimum is infinity, positive infinity. That's a very standard thing. Now, if a number is x, think about it. You have to find the log of it, no? So 4 will go to log 2 bucket, no? Which is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So the bucket that is lies in, the 0 is the bucket, 1 is the bucket, 2 is the bucket, 3 is the bucket, is basically determined by the floor of log. Okay, floor of log of any number. So you find the floor of log of a number using this built-in CLZ2. And then you can find out which bucket it lies in, and you can add, since this is like constructor for it with a single element, you can add it to that small bucket. That min over there is only going to change. And then you have build of segment tree where you merge with sums being added and minimum being minimumed together, right? Because if two nodes get merged, the minimum in that bucket will be the minimum of 2. And that's how you merge basically, and you write the standard build query, right? And when you want to find the answer for L2R, the way you do it is you find the merging of that segment L2R. So now you have the sums in each bucket and the minimums in each bucket. And then what you do is you like if the first trivially find out if the answer is 1 or not. If not, then you start from 2 to the power 1 bucket and see whatever has been added till 0 bucket, 2 to the power 0 bucket, if that suffices. So if the prefix sum already covers like is less than this element, so it is in this range, you have to see that this needs to be sufficient, right? So you check for this, like prefix sum plus 1 is the element that you are seeing, that you want to check if it exists or not. Okay, and if it is this in this range, then only you check this range, or else if the previous element itself suffices this much, then you don't need to check it. If it is in this range, if it is less than the next power, and the current segment's minimum is bigger than this, so there is no way to create this element. That's what you look for. So in that case, that is the answer, or else you keep going forward in the buckets and somewhere you will get the answer. If you didn't get it in 30, every number is present, then like you can build every number using the prefix sums, and prefix sum plus total prefix sum plus 1 will be the answer. Right? That's the idea that you use. Now this is the full code for this. The problem with this code is you will get a TL if you submit this code, right? So this problem on CSES has a very strict time limit. I tried optimizing this code using converting it to arrays and stuff, but it was still very, very, very on the limit. If you have to get it passed, what you'll have to use is 2n segment tree. Basically, you have to use iterative codes of segment tree, right? I don't want to go into doing that. Another idea that you can use is maybe you can use prefix sums to get the sum of range, and then sparse table to get the minimum of ranges, and then you can do this in faster complexity. But then that is something I'll leave as a task for you to solve. If you could understand till this much, most probably you should be able to know how to do prefix sums and how to do sparse tables in WOF once, right? So that will be something that I'll leave to you. But then I hope you understood a really interesting idea that how can you find what is the first number you cannot create. This is an idea in itself. And if you know this, maybe someday you will get this question and you will be able to solve it. That's how you build your repertoire of ideas about greedy, right? You have to know so many ideas. So that will be all for this episode. I hope you enjoyed learning some of it, even if not the last query version. I hope you enjoyed learning this first version over here. If you like this idea of creating videos on greedy, give it a like comment, okay? Because creating these contents are super hard, whereas YouTube kind of rewards people who create roadmaps and how to crack Google. So I'll see, maybe those are videos that maybe needs to be created, but I feel a lot of people would genuinely be benefited if more such content comes out, right? So if you encourage these, only then this will be created. So give it a like, subscribe to the channel, and then I'll see you in one such next video too. See you all. Bye-bye.